level language program, you can get an optimum output. So in that case, you can mix up some assembly language code along with the C code. And similarly, when accessing certain low-level hardware, right, that may not be possible with the high-level language program like C. And in that case, we can go for this assembly level language program that is embedded inside the high-level language program that is possible here. And mixing C and assembly is little complicated, right? Mixing a C language program, which is a high-level language, and assembly level language assembly is actually a little complicated. And the programmer must be aware of how the parameters are passed from C to program, because whenever some task is converted, right, from C program to assembly level language program, some data need to be processed from C to assembly level, and upon exiting, the output from the assembly level language program should be brought into the C program. So this data passing the parameters and data may be a bit difficult, right? So that is what, and the method of invoking the assembly routine from the C code is, again, it depends on the cross compiler what we are going to use it. So one example is again C51 cross compiler. So there are two commands. Of course, this is for 8051, which may not be useful for your case, right? So there are some commands like src directive called pragma src. So that is actually should be the top of the file. That should be the first line of the file, so that the C compiler generates an src file instead of an object file, right? So that will generate an .src. It's a source file. Now compile the C file. Since the src directive is specified, the src file will be generated. Now the src file contains the assembly code generated for the C code you wrote, and rename the src file as a A51 file, and this A51 file is inserted in the assembly code, right? You write a C code, and using this you can convert it into .src file, or and this program will be just, you can embed this in the normal assembly code, right, where some part of the other executions are done. So this is actually an example. The first line starts with pragma src, then some C program has been written, right? And this C function on cross compilation generates the following assembly level src code. The special compiler directive src generates the assembly code corresponding to the C function, right? So here actually what we have done is return the value is argument plus 1, so that will be added, and this will be of course returned upon calling this particular function. The function name is my assembly function, right? And mixing the code written in a high level language like C and assembly level language is useful in some scenarios, of course, and the source code is already available in the assembly language, and the routine written in the high level language needs to be included into the existing code. So here actually what I am going to do is mixing the assembly level into a high level language program. The entire source code is planned in assembly code for various reasons like optimized code, optimal performance, efficient code, and proven expertise in the handling the assembly, etc. But some portions of the code may be very difficult and tedious. So in that case, those sections of course will be written in C program, and that can be embedded into that. For example, a 16-bit multiplication using this 8051, right? And to include built-in library functions written in C program provided for various compilers, cross compilers. That is, again, we can go for a mix-up of these two things. For example, built-in graphics library and string operations. So these two things, either a graphics library or using the string operation is it can be easily done in C, which is very difficult to do in the assembly level language program. So in that case, we can suitably combine a assembly level language program into a high level language program. And most often the functions in return C use parameters passing to the functions and returns the value to the calling functions normally, right? So whenever there is a function is called, some parameter will be passed, and upon executing some parameters will be returned back to the main function, right? And the parameters are passed to the function and the values are returned from the function using the CPU register, stack memory, and the fixed memory. And its implementation in cross compiler is cross compiler dependent, and it varies across the different cross compilers. And this is one example like Kale C51, right? So C51 allows passing of maximum 3 arguments only through the general purpose registers R2 to R7. And if the three arguments are of character type variables, they are passed to the functions using registers R5, R6, R7 only. And if the parameters are integer values, they should be passed through the register pairs R6 and R7, R4 and R5, or R2 and R3. So there are some restrictions while passing the data between the assembly level language program and the high level language program. And if the number of arguments is greater than 3, the first 3 arguments are passed through the registers and the rest are passed to the fixed memory locations. So you put the data in some memory location, and in the C program you take the you read the data from that particular memory location, right? Already you should be knowing, right? Pointers are available for C programming, and you can straight away access the memory locations using an assembly level language program. So this is very well can be done there. And what about the return values? So once some program has been executed, now the C program should return some value. So R7 is used for returning the character value, or R7, R6 will be used for returning the integer value. And the C subroutine can be invoked from the assembly level language program using some functions like lcall underscore C function, right? The C function is actually the program that is written in C language. And the prefix underscore informs the cross compiler that the parameters to the function are passed through the registers, right? So if you start with an underscore, then that shows the parameters are passed through the registers. And if the function is invoked without this underscore prefix, then it is understood the parameters are passed through the fixed memory locations. So if it is underscore, then parameters are passed through the registers. If it doesn't have any underscore, then using the memory locations, the data transmission has occurring. And after these two things, the third type is actually the inline assembly language program. So we have written a C code, and in between we can embed a few lines of assembly level code into it. Again, there is a C51 case, right? So this pragma ASM, so that shows this is actually the starting of the assembly level code. And you will be writing some assembly commands, and finally a pragma end ASM, that shows here my assembly level language program is ending, and the C program will continue like that, right? So that is again happening by combining a C program into an assembly level language program. And instead of normal C, we can also make use of this embedded C. Whenever the conventional C language and its extension are used for embedded systems, it is used as an embedded C program. Say for example, some commands, some part of C programs which is useful for embedded system applications. And the programming in embedded C is quite different from the normal C program in a normal OS. So desktop computers contain working memory in the range of megabytes, but here are megabytes or gigabits, whatever it is. But here in the case of microcontroller, it will be having very limited amount of memory that is available, right? So almost all embedded systems are limited both in storage and working memory resources. So embedded application developers should be aware of this fact and should develop application in the best possible way which optimizes the code memory, right? Because in your computer you will be having plenty of memory, both RAM as well as ROM. But in mobile applications, that is going to be very, very minimum. So in that case, the programming has to be done in a more effective way. And in other words, the hands of an embedded application developer are always tied up into the memory usage context. And this is actually a comparison between the C and the embedded C. Right? C is well structured. Embedded C can be considered as a subset of C programming. C offers a combination of high-level language and assembly level program and hardware access. Everything is actually possible here. Here the embedded C supports all C functions and incorporate a few target process specific functions are also available here. And here the conventional C language follows ANSI standard and it incorporates various library files. Here again the standard ANSI C library implementation is always tailored, but it is tailored towards the target processor which we are going to use. And here a platform specific application known as compiler is used to do the conversion of programming from C to a high level language here. And in the case of embedded C, we will be using a cross compiler. Instead of a compiler, here actually we are going to use a cross compiler, and which will be running on a system but not for a same processor but for a different processor that will be cross compiled. So this is of course a general idea about the C program and the embedded C program. And what is the difference between a compiler and a cross compiler? That again of course we are going to see now. A compiler is a software tool that converts a source code from a high-level language into a machine-level language, right, which will be understood by the system. And the cross compilers, of course, does the same thing, converts again, but not for that particular process. Again, that was the example actually I was saying. I am writing a program for ARM Cortex processor, but as such I am developing the program in the Intel processor in my laptop. So my Intel processor should develop a program that is compatible to run on a ARM Cortex processor, right? So the compiler should be compatible like that. So in that case, we have to go for a cross compiler. And the source code is converted to target processor specific machine instructions. Here actually, I think we will just go through, right? Instead of comparing this point by point, we will just go through what are the points so that you can get an idea about this. And the development is platform specific, right? Which OS we are going to use. It depends on that compiler. And say for example, the C compiler will be different for Windows OS, Linux OS, or whatever may be the OS that you use, right? And a native compiler generates machine code for the same machine in which it is running, a native compiler. But cross compiler, it is going to develop an application for a different processor. And in cross platform development, the compiler running on a particular target processor or OS converts the source code to machine language for the target process whose architecture instruction set is different from the processor on which the compiler is running. I think this word gives an idea about what is a cross compiler. And embedded system development is a typical example of for cross platform development, right? So we are writing a program, Android, Java, right? So we are actually using an Android Studio. We are developing a program and testing the program on the laptop using Windows, but that program will be running on an Android OS. Right, so there are two different compilers are coming here. And the C51 is an example for the cross compiler. And in embedded firmware application, whenever you use the term compiler, it normally refers to a cross compiler. I think with this we have almost concluded the module number 4. Thank you.